Barciej Żupański and Marcin Golec, PhDs, are going to play for us today. This is the first meeting, a special undertaking organized by the University of Silesia in Katowice. And what are we going to talk about today? Well, in this first meeting, we'll be talking about particles, which are much more difficult to see than ghosts, if there are any ghosts at all. In a moment, we will have Professor Jan Kisiel, a nuclear physicist from the Institute of Physics of the Silesian University of Silesia. But before that, I'd like to ask Professor Ryszard Koziołek to approach the rector of the University of Silesia. All right, what happened, Mr. Professor? You know, everyone is at home and we're trying to launch a new event. Yes, we have been using the fact that we are quite used to having some public events taking place online. Yes, it's a lesson we've been learning all the time. As a university, we've passed this test quite well, but I'm still certain that all these problems should end as soon as possible for the benefit of everyone and of the university. Probably students who are taking part in online classes would agree with you, but you know, these are the times. Yes, we will survive also thanks to science being the hero of this meeting. Yes, we want to talk about science, we want to promote what's going on in science. At the University of Silesia, yes, that's the very idea of these meetings, of the scientific premier stage, to show scientists on a regular basis, not just once, but systematically, to show what we publish, what we discover, what we research, what research and scientific programs there are. That's one. And we want to do it for ourselves a little, because of some egotistical reasons for the university to show off as a university, but also to show ourselves to us. We have over 3,000 employees in our university, and that's why we do not all know each other. Sometimes, you know, we do not know what other people from our own discipline are doing. And so I was thinking that maybe the university should look at itself, its diversity, its richness of its research. That's one. And the second reason is more serious. We want to show the society what science is today, and to explain it in a way that is clear, that is easy to understand. Since I remember, there has been a discussion on how to connect science and business. And it's one of the ideas, because people who have some capital are going to look at, to see this program, and maybe they will come up with some commercial ideas. Yes, sure, yes, commercial or utility ideas, because nowadays science appears in every area of our lives. It would be difficult to imagine living without science. Most functions, most items, things that we do in life originate from some scientific discoveries. And maybe many of them are just appearing now, and the works of our researchers will demonstrate newer and newer undertakings. Professor Ryszard Koziołek, ladies and gentlemen, thank you very much. Professor Jan Kisiel, a nuclear physicist from the Institute of Physics of the University of Silesia. Ladies and gentlemen, this is the cover of a very prestigious magazine, Nature, from the April of this year. The mirror cracked, about symmetry in the universe, and that's what this article is about. The author is Professor Jan Kisiel. So, Mr. Professor, what does it feel like to be on the cover of Nature? Well, it's very important to say that this was an international group of physicists with over 300 scientists, including about 30 people from Poland, from several universities, from Warsaw, Krakow, Wrocław, and from the Institute of Physics of the University of Silesia. So it is not just my publication, I'm just a co-author of this publication. But it is, yes, it is a very prestigious magazine, that's true, for physicists, not only, but for scientists in general, from scientists from exact scientists, and we're quite proud to be able to demonstrate our research we have been conducting for more than a dozen years, to have it noticed and presented in this magazine, and a fragment of our detector we are going to talk about is on the cover of this issue. So this is the detector, which is visual, is really splendid, and we'll go back to it in a moment. I'd just like to pay your attention that on YouTube you can ask questions to Mr. Professor here using the chat option, and we can see your questions on a continuous, regular basis. I think we should start by saying about these particles. The particles which are very very light, because in every second billions of these particles strike through our body. Yes, that's true. Neutrinos are matter particles which are most common in the world. I mean, photons are most common, but when we have particles that have mass, neutrinos are most prevalent. The discovery of their mass was awarded with the Nobel Prize in 2015, and they are the most common matter particles. And as you have said, when discussing here today, every second, on 1 square centimeter of our body, 100 billion neutrinos from the sun go through our body. We have evening now, so we have fewer neutrinos. They also pass through our planet. They are so weak on the matter, it doesn't matter whether the sun shines from the top or from the other side of our planet. More or less the same amount of neutrinos pass through our body. But it's not the only source of neutrinos. We also have neutrinos produced in the atmosphere. As you know, Earth is surrounded by atmosphere, and luckily, otherwise we would have no life on Earth without atmosphere. And the particles from the original cosmic radiation hit the nuclei of nitrogen and oxygen, thus producing neutrinos indirectly, which also reach us, which our planet. A very strong source of neutrinos is a nuclear reactor, where atomic nuclei are dissipated. We are sources of neutrinos ourselves. In the body of every person there are several dozen milligrams of potassium-40. That's a radioactive element which has a very which continues to live in our bodies for a very, very long time, and it also emits neutrinos. So yes, but it's very difficult to see them, to notice them, to catch them, isn't it? That's true. We can register particles that affect matter, and which affect the matter, the material of our detector. And we can register them only if these particles, as I said, if they can be detected by our detector, and the probability of of the impact of neutrinos on matter is much lower than that of any other particle. These are billions of times lower probability, and that's why to observe neutrinos it requires large detectors. I'm sure we're going to go back to Super-Kamionate detector, and it has to take a long time because we have very few neutrinos that can be registered. And third, these interactions, and third, these neutrino detectors are placed deep underground so as to avoid cosmic radiation background. So we could compare it to a situation where we are in a room where everyone is talking loudly and we want to hear a whisper. Yes, yes. It is a good comparison. And you can add only if you have a very good hearing capacity, because the probability of neutrino interactions is very low, but luckily they do interact. So let's go to this amazing place, the Super-Kamioka detector, which is placed at what depth? It's about 1000 meters. Not under the surface of our planet. That's not true. It's inside a mountain, but you might say that over that detector there is over 1000 meters of rocks which perfectly limit cosmic radiation which reaches that detector. So you try to find a silent place and then you'll be able to hear the whisper. Yes, it has to be black, no light, filled with pure water. Yes, it's a gigantic cylinder of the height and width of about 40 meters, filled with very pure, regular pure water. And around this cylinder there is over 11,000 devices, photoreceptors. These are the golden balls of the width of about 50 centimeters. These photomultipliers are devices that allow us to register single photons. Single photons, which is a very little amount of light. So when light hits a photomultiplier, that signal is then multiplied many times. And after leaving it, we then have an electric signal that is very easy to measure. How many such signals can these photomultipliers register? How many millions? Well, so there are several hundred or several thousand per year. So in this experiment there is no problem with registering the particles. All the particle interactions which are recorded by the detectors, basically we can measure almost all of them, but there are quite few of them. So unlike the Great Hadron Collider, where we have a rain of particles, most of which we know nothing about. Some fit our model, while here we have a reverse situation. We have events taking place very slowly and in silence. Yes, complete silence. In these experiments, we have to even apply proper software or even proper equipment to just catch the signals that we're interested in. And if we can, otherwise it would be very difficult to measure all those particles. But going back to Super-Kamioka, the situation is very different. We have few interactions. Naturally, there are also other interactions which are background interactions, but we know how to differentiate between the former from the latter. The background is low because it's very low. Have you had the chance to be inside? Yes, I had the opportunity to work using a rag to clean this detector. It is a cylinder made of steel, and last year water was eliminated from it, you know, so a lot of water. And the physicists from this experiment, everyone had 1 week to clean the walls of this detector so that in the future it can operate even better. Because as I have already mentioned, it's pure water. We want to avoid any light losses in front of the photomultipliers, but after many years this water is eliminated, discharged, not every year but every several years, and then it requires regular cleaning. Also damaged photomultipliers had to be replaced. Just to remind you, you can ask questions to our guest of today. The questions concerning neutrinos and this amazing detector. A question from my daughter, who is 15 years old, and she graduated from the same high school as you did. She asked me, how are they able to keep them clean? There is so much water. Well, we have a proper water cleaning system, water treatment system. Water is filtered many times in a continuous manner, but not in a, let's say, a sudden manner. Water goes into the detector from one side and goes out of it on the other side. So the water that is discharged is then treated, cleaned again, and it goes back to the detector. So, you know, it's a large, significant infrastructure for dosing water and for purifying water for this detector. All that to have the signals which are recorded, to make them as strong as possible, because there are not many photons which we can record. In a moment we'll tell you about a certain catastrophe which was not beautiful, but it was grand, and which for a moment put the entire project at risk.
Drodzy Państwo, dostałem informację, że pytanie do pana profesora można zadawać za pośrednictwem nie YouTube'a.
You can ask questions using Facebook, not YouTube. Just to correct this piece of information, Professor Jan Kisiel, co-author of an article published in the Nature magazine. Please tell me about the 2001 catastrophe. What happened? Looking at these photomultipliers, what happened again? Yes, the catastrophe took place almost exactly 19 years ago. It was November 2001. What happened was 60% of these photomultipliers, in total there are over 11,000, 60% were destroyed. There was an implosion inside the photomultiplier. There is vacuum, and we suspect that one glass cover of one of these photoreceptors didn't make it. It imploded inside, and a wave took place which destroyed completely 70% of these photomultipliers. So it was a chain reaction, exactly. These photomultipliers were broken because they have a glass dome. Everyone has a glass dome. The golden thing that you see, it's the glass dome. These were broken. Some fixtures were also damaged. And as I said, over 60% of all the photomultipliers were affected. And so I know everyone was really scared, but several months later it was they recovered. Yes, luckily it took about 2 years, because the experiment started to operate several weeks ago with the photo multipliers that were left, because you know light can be recorded by 11,000 photo multipliers or by 3,000 photo multipliers. Now, naturally, if you have just 3,000, then you have a much poorer signal, but well, you can work. So it was a gigantic cost at that time. $3,000 was the cost of one photo multiplier, and you had to replace over 6,000 of them, plus produce them, because you know it is not so quick to produce them. Yes, you do not produce in a factory in Taiwan. Yes, that's true. The Japanese made a decision right away to recover this experiment, and it was. The photo multipliers were replaced, and they were given additional acrylic covers to avoid a similar situation in the future, because you know it's 140 cubic meters of water. There is a gigantic pressure. So these photo multipliers have to stand a lot. Mr. Professor, when I was in CERN, I heard a joke which was told among physicists. The neutrinos were a negative hero here. After it was published that a result of an experiment conducted by CERN, it turned out that neutrinos can be faster than light. And you know, very soon it turned out that it was just an error in research. Someone made some mistake, but the joke was, we do not serve neutrinos. A neutrino walks into a bar. Yes, yes. A group of physicists from our university participated in the measurement, or in two measurements actually, which were performed, one several weeks and the other one several months after the experiment. And in our experiment we managed to measure that the speed of neutrinos is the same as light signal. So we demonstrated that neutrinos are not superluminal. So they are close to light speed because they have minimum mass. This is an important thing. Let's go to this issue. This title, The Mirror Cracked, does not refer to the catastrophe of 2001. It refers to symmetry. When our universe was born, there was the same amount of matter and antimatter. But we are living in the world made up of matter. So this symmetry had to be, let's say, violated at a certain point. What does it have to do with neutrinos? Well, all scientists agree that when our universe was born, there was an equal amount of matter and antimatter, while now we only have matter. And to produce antimatter, for example, on Earth, we have to make a lot of effort. So what had to happen is, well, the world had to become made of matter and not symmetric in terms of matter-antimatter. In the 1960s, Soviet physicist Sakharov gave three conditions. The famous Sakharov's conditions, which are commonly adopted by physicists, which, if met or if explained, then will be closer to the answer of why we have matter now, not antimatter. And one of the conditions was violating the CP symmetry. CP symmetry, well, in physics, symmetries are very important. We make use of lots of symmetries in the laws of behavior, which allows us to interpret the results of measurements or to understand what we observe. This symmetry is a symmetry of duality. So if we put something to the left or to the right, it should look the same. And C symmetry is a charge symmetry. So if we replace a particle with an antiparticle, we should have one positive and one negative particle. And the CP symmetry was observed for quarks. That effect has been known in physics for about 50 years. So this is what Sakharov said. The CP symmetry should be violated, but it turns out that this violation for quarks is too poor to explain this gigantic asymmetry between matter and antimatter. So where to find this asymmetry? Well, if it's not in quarks, maybe it will be found for different particles, leptons. Quarks include protons and neutrons and many others. While leptons, an example of leptons are electrons. It's a different family of particles than quarks are. So an electron has an electron neutrino and a muon. It is another lepton. If it's 200 times heavier than an electron, it has its own neutrino, the so-called muon neutrino. And what we measured in our experiment and what was published in this article, well, we asked ourselves the question, do neutrino oscillations look the same as anti-neutrino oscillations? It was possible in this experiment in the T2K, because here we use a beam of neutrinos produced in the Japanese accelerator center, situated about 150 kilometers to the north of Tokyo, and there it is possible to produce both a beam of muon neutrinos that are made of matter and antimatter. And the second detector, which is visible on the cover of this issue, is situated 295 kilometers away in the Kamioka city. So, in short, Mr. Professor, you produce neutrinos in the accelerator. They fly towards the detector, and there you try to see them, to perceive them. Yes, just to be more specific, the accelerator produces a beam of protons, which, when hitting a shield, we have graphite shields. Different particles are produced, among others pions, which split into neutrinos, and these neutrinos are sent first to the NT280 detector, situated just 280 meters away from the production site, while the other Super Kamokande detector is situated 295 kilometers away from the neutrino production site. We'll go back to this experiment in a moment. I'd like to just remind you that you can ask questions on Facebook, and Mr. Grzegorz asks, Mr. Professor, what can we do with neutrinos? We know they exist, we can measure them, but can we use them practically and use their properties practically? Well, I answered that question to some degree already, because I said that it's very difficult to measure neutrinos. The detector we used to measure the Super Kamioka, it is 40 meters of diameter and 40 meters of height, and that's where we measure, let's say, several hundred or several thousand neutrinos per year. I think what he means is practical applications. Well, I can put it like this. In 2012, an experiment was conducted in the Fermilab. Fermilab is a particle physics laboratory in the US near Chicago, and they also produce neutrino beams. And in 2012, they conducted the following experiment. A neutrino beam produced in the Fermilab was sent to a distance of about 1,000 meters to the Minerva detector, which measured the neutrino interactions, and the intensity of that beam was 10 to the 13th. About one neutrino could be recorded. 10 to the 13th means 10 with 13 zeros, and only one neutrino was recorded in the Minerva detector. So we can see few of them. Yes, we can see few of them because the probability of interaction is very low. And that detector was just, 1 kilometer away, while our detector is almost 300 kilometers away. But going back to the Fermilab experiment, they were able to register one neutrino. What they did is the pulsating beam, the pulse was very short, nanoseconds, so 10 to the minus 9th of seconds. And the word neutrino, the 8-letter word, was split into bits, like we do when we send information. Well, we use electromagnetic waves, and it was recorded in the Minerva detector. So if there was an event, it was 1, and if there was no event, it was 0. So it was communication. Yes, exactly. But this speed was below 1 bit per second, so it was very low speed. They were sending one word for 2 hours, but the positive effect of that experiment was that there was only 1% of error. So this word was decoded very well by the Minerva detector. Yes, Mr. Professor, if I can interrupt, theoretically we can imagine a situation where we could send a signal using neutrinos from one point of Earth to another without using satellites, without sending it 38,000 kilometers up and down, but maybe we could send them through the Earth core. Yes, we could, because as we know, neutrinos have a very weak effect. It's very important to emphasize they have a very small effect. We can use them to send signals without losing much, but to record that signal in this other place, we will need a gigantic detector. Note the numbers from the Fermilab experiment. There was just 1 kilometer. There was a very intensive beam of neutrinos, the production of which requires a gigantic accelerator and a gigantic detector. It was 170 tons of oscillator, so an expensive sending machine and an expensive receiving machine. Yeah, that's true. So it's difficult to imagine how we could apply this in the foreseeable future. But when Bell invented telephone in the US, well, 4 or 5 years later, there were several dozen phones being used from discovery. And the first radio transmission over the Atlantic, it was only 1 letter long. Yes, so let's be patient. And let's go back to this experiment. Neutrinos and antineutrinos are different. Can we say so? Well, just like a particle and an antiparticle are different. But what we mean is that they behave differently. Yes, that's true. There is a difference. In physics, we know particles and antiparticles, which have the same properties or the same mass, such as mass, spin, and opposite charge. That's the difference. But in this experiment, well, neutrinos, the property of neutrinos is that they can shift while traveling in time or in distance, over distance. We call it neutrino oscillation, this phenomenon. And for discovering that neutrinos have mass, because the neutrino oscillation phenomenon can only take place when neutrinos have mass. So if you can observe neutrino oscillation, then you know that the mass of neutrinos is more than 0. Unfortunately, we are not able to say what the mass is, how many grams or how many electron volts the mass is. But what's a very important achievement resulting from this experiment of 2015, the experiment by McDonnell and Kate, what was his last name? The results are important, yes, yes. Exactly, we apologize to the authors, yes. Takadi, I should remember it, because I worked in that team, so I should remember this. And they were granted the Nobel Prize for discovering neutrino oscillation, and that's thanks to them we know that neutrinos have mass. And again, so many side notes, they are quite necessary. Going back to this article, what we did in our experiment, in the T2K experiment, we are able to use neutrinos and antineutrinos, and we shoot neutrinos and we analyze their oscillation. So how many neutrinos were received? We can check this in the detector. Then for many months we shot anti-neutrinos, and we try to see how many of these anti-neutrinos can be detected in the Super-Kamioka detector. And when neutrino oscillation, if neutrino oscillations were the same as anti-neutrino oscillations, then we could say that the CP symmetry for leptons is provided, because neutrinos are examples of leptons, while we observed that electron neutrinos oscillate much more frequently than electron antineutrinos. Do you know why? Well, maybe it is a property of the nature that surrounds us, of the environment, because violating CP symmetry is described by the parameter in physics. It's called delta CP, CP meaning violating the CP symmetry. And the parameter that resulted from our experiment indicates and to emphasize again, it indicates, we're not certain, we have too few examples to call it a scientific discovery. It indicates that CP symmetry could be violated in the lepton sector for neutrinos and anti-neutrinos. Ladies and gentlemen, in a moment we will go to Japan, and I'll try to use to say something in Japanese. Arigato, arigato. And how is your Japanese? Oh, quite poor. This word was just half of all my Japanese words that I know. Alright, so again, just to remind you, using Facebook you can ask questions to our professor here, who works in an experiment connected to neutrinos. Please ask questions, and after today's meeting you will have a chance to talk using Zoom. Am I correct to understand that not only is the country exotic, and the place is too? Well, to some degree that's true. It's not my first experiment in high energy physics or neutrino physics. In every case, these teams were international teams. This one was my first experience in with Singapore teams, and they work differently than, for example, scientists in Italy. In Japan, in Asia, you set up a plan, and it is followed very specifically, point by point, step by step. The Super-Kamioka detector is well, the incident was in 2001, so it has been operating over 20 years, but the NE280 detector, the short range, it was constructed from scratch, mainly by groups from Europe, including from Poland. So a schedule was very specific, with 1 week detail, and it was followed. It was constructed in time. Everyone provided components on time as planned. So I think that is something that that we can learn from, not only in physics but also in other areas. But is there a very specific atmosphere? Because I know that in CERN, you can feel that you're a part of a certain society group connected by some ideas. Yes, in Japan it's the same. You can see it clearly in the dining room where everyone eats together. People who operate the accelerator, the professors, maybe Professor Kajita eats at the same in the same dining room as others. We meet in different places, restaurants, places like that. So you can really feel an atmosphere that I really like, a direct atmosphere. You can always talk to people. If they don't have time, they'll tell you, I'm sorry, I don't have time, let's meet in 2 hours or tomorrow. And you can really approach anyone. And I don't know, it's only limited to the world of physicists, but well, it's very nice, a very nice feeling. Astronomers also like neutrinos one day, because you said that in the large dark detector it's very silent. Sometimes you see some light, maybe once a day if you're lucky enough. The Cherenkov's radiation. One day there were several dozen lights. The astronomers found out that in the sky you saw a supernova explosion. Yes, this took place on the 23rd of February 1987. On the Earth there were 3 neutrino detectors, the Kamiokande, the one that was before the Super Kamiokande, a USSR detector in the Caucasus, and a detector in the US. And the 3 detectors at the same time, because later on time synchronization was conducted, but it was confirmed that everyone over 2 or 3 seconds recorded between 8 or 10 cases, which is a really high number, a gigantic number to record several neutrinos over 1 second. That's very rare, very rare. And it turned out these neutrinos originated from a supernova explosion. That supernova was called 1987A in Magellan's, yes. And despite that, such a gigantic number of neutrinos reached us from very far away. So it was very spectacular, and these were the neutrinos which covered a distance of dozens of light years and flashed in that water. Yes, from the Magellanic clouds. Yes, they did spark up in the 3 detectors. A supernova like this emits many more neutrinos than our light over its entire lifetime. So it was a gigantic attack of neutrinos over a short period of time. Now we are waiting for another supernova explosion. We have Super Kamiokande operating. We have detectors in the US. So if an explosion like that takes place, naturally it depends on distance. Let's say, let's hope. Once every 100,000 years. Oh well, we will see. I've heard some estimations that in our galaxy there should be between 1 and 2 supernova explosions per century. But you would have to get more statistics to calculate that. But chances are that something will be possible to observe. We have 2 questions, so please answer in a few words. Jonna, how to explain to children what neutrinos are? Well, it's a good question. I'd like to know that, the answer to that. What can you say? These are elementary particles without charge, but with mass. And they are matter particles of matter. And they make up what surrounds us. What else? We do not really know what mass they have. We know they do have mass, but we do not know what it is. There is also a Katrin experiment in Karlsruhe in Germany, and we hope it will be able to measure the absolute mass of neutrinos with the exactitude of 10 times more than currently. Right now we only know the upper limit of electron and neutrino mass. We know it's lower than 2 electronvolts. I'm using my smartphone not because I want to play a game, but because I want to use it as a prop of sorts, because Mr. Marek said, what do you think about the Credo project? Just to remind you, every owner of a smartphone like that, you can install an application in the background, and when we do not use our smartphone, the myons which hit or go through the screen of our smartphone will be recorded. Can we use that in neutrinos? I don't think so. Not really. The probability and the stream of these particles are of electromagnetic part. Myons have charge, muons have charge, so a particle that has a charge, it's quite easy to register, and a detector does not have to be very large. You have special traps you can construct at home. Yes. A muon detector is quite easy to construct. It can be small, as you can see. It's a very interesting project, the Credo project, because it allows you to participate in the fundamental physics and particle physics research, and it allows to demonstrate to the population, to the society, that this is something that surrounds us every day. We will never eliminate the muons that we have, and we can research them. At the end of our conversation, I'd like to ask you, what is the condition of physics of today? Because it seems that there is, the particle physics, because we collect lots and lots of information, not in the case of neutrinos, but in general. And what do you think? Is it going to be more and more difficult to discover new things? It seemed in the past that discovery of Higgs boson would be a key to the door that will open physics for us, while it turns out that the further we go, the more difficult it gets. Yes, the Higgs boson discovery, well, it was an expected event, so it only confirmed what the particle physicists had been expecting. If there was no Higgs boson, the situation would be more interesting. This discovery confirmed the standard model. This theory describes the elementary interactions in a specific way among elementary particles. So maybe the experiments in LHC, now it's going to be modernized, this infrastructure, and the 4 detectors also. So maybe in 2 or 3 years we are going to have some new results, but well, we have a certain difficulty now. You're right, because to construct a next generation accelerator, a larger one than LHC, to go even deeper into the matter that surrounds us, that's gigantic cost. What's the size of LHC? the circumference is almost 27 kilometers. That's magnets where we have helium. So these are. So it's more complicated than the International Space Station. Maybe it is. Maybe it is. And when a TGV is going through the Geneva station, which is 10 kilometers away from LHC, it introduces some disruptions. So it's a very precise device. But if you want to research Higgs particles, well, another unsolved problem is the search for dark matter. We know that there is matter is missing in the universe. So maybe some heavy neutrinos will answer some questions regarding dark matter. That's why it's so important to determine mass, because if we know neutrino mass, we could try to estimate something. Is that correct? Maybe it would fill in the missing mass of the universe. Yes. There are a lot of hopes concerning the Catherine experiment. If it turns out that the mass of neutrinos is lower than 0.2 electrovolts, as we know, the limit is 2 electron volts, and if it turns out that the mass of electron neutrino is lower than 0.2 neutrino volts, then there will be no results. We'll have a better estimation for neutrino mass, however, which will also make the other space estimations. Very often we are asked why we spent billions of dollars for such research on Kamiokande or Super Kamiokande or CERN, but the answer is clear. We try to find the answer to the question where we come from and where we are going. Yes, people have been interested in finding such answers for since always. Maybe we are missing something. Maybe we have to go different ways. But some fundamental research requires funds, which sometimes we can recover. It cannot be eliminated, because in CERN the www protocol for sending websites was discovered, and all the CERN discoveries are public. So CERN became public property for 0 zloty, 0 francs, and so maybe these experiments being conducted in particle physics will be used in the future. As a result of the Apollo program, not only do we have several 100 kilograms of material from the moon, but also the IT revolution. Yes, the LHC, the liquid helium installation, is a significant technical achievement to have so much liquid helium, to maintain it for so many years. Well, maybe one day it will be used for something. There is an anecdote about Faraday, who over 150 years ago discovered magnetic induction, and when he had a lecture on that subject, one of the lords asked, what practical applications will there be of that? Faraday replied, for now, I don't know, but I'm sure you will put a tax on it one day. And today we all pay the taxes on Faraday's discovery, because we use electricity. And we're talking about sending information using neutrinos. Well, physicists demonstrated it is possible. Naturally, the speed or the error has to be taken into account. We have gigantic detectors, gigantic accelerators, but still, the physicists in the US demonstrated that it is possible. So maybe in the future it will be used. Maybe there will be some revolutionary discoveries in detector technology to record even smaller neutrinos. Professor Jan Kisiel, a physicist from the University of Silesia, will be at your disposal right now at the Zoom platform, and the link for asking questions can be found on Facebook. And now I'd like to ask our band to play something, and Mr. Professor, please answer some questions. Thank you very much. That's Marcin Żupański and Wojciech Golec, PhDs. Thank you very much. It turns out that even in online transmissions, where we're able to produce a very warm and cozy atmosphere, which is especially hard to do and very important in this season. And I'd like to thank Professor Jan Kisiel, who answered your questions on Zoom. I'd like to thank the Miejscownik bookshop. And that's the end of the scientific premiere stage of the University of Silesia. See you next time.